Ready to start?
Yes. Yes, absolutely. So you're very lucky to have him. So sensitive information in a networked world. So when we actually submitted our pre-proposal in 2000 to the large ITR program, we called this sensitive information in a wired world. And as time has gone on and fewer networks are wired, we decided to get rid of that word, which was being used in a metaphorical sense, but the metaphor doesn't make sense anymore. Okay, so after getting the grant, we decided to come up with an acronym for it. And the purpose of the study was to do a very broad-ranging, so 5-year multi-institutional, multidisciplinary, multimodal research project on sensitive information. Now, multimodal means we're doing theoretical work, algorithmic, sort of theoretical computer science work. We're doing experimental work, building software, all of which is available for download from this website. And we're also doing truly multidisciplinary work on public policy, law, ethics, et cetera. So I'll touch on all of that a little bit. So we decided to come up with an acronym. We were later told by the then Cyber Trust program director, Carl Landwehr. It's now Carl Levitt. Carl Landwehr, that it's good not to put an acronym in your grant proposal. That often there's people who just really don't like a specific acronym. So he thought it was a good move to come up with an acronym later. So we came up with Privacy Obligations and Rights in Technologies of Information Assessment, Portia. Portia happens to be a self-trained lawyer from The Merchant of Venice, a play by Shakespeare. And one of our research partners is a constitutional lawyer at Yale Law School. There's an anecdote about this acronym, which I can tell you at the end if you remember and if I have time. But one thing I want to say is, because the first word is privacy, a lot of people think the whole project was supposed to be about privacy. That was never the intention. This was supposed to be a comprehensive, multifaceted look at sensitive data. So what do I mean by that? So the motivation, going a little more deeply into what was the motivation for this huge, sprawling project, which we're now in the 5th year of, and which has probably involved at least 100 people, maybe more, at 5 institutions, plus 5 universities, plus all the partner institutions. The motivation is that the increasing use of computers and networks in everyday life has led to an explosion of sensitive information. Now, what do I mean by sensitive information? I mean that information, if it is used improperly, can harm at least one of the stakeholders. The data subject, the data owner, the data user, whatever. So what's very important is that you realize that not all sensitive information, sensitive in this sense, not all sensitive information is strictly private. Okay, so in the sense that confidentiality is the issue and breach of confidentiality is the only possible harm. So according to this notion, copyright works, for example, are sensitive information. There are very precise rules, actually not very precise, somewhat precise rules by which copyrighted works are supposed to be used. And if copyright law is violated, the copyright owner can suffer quite a bit. So can the distributor, and so could the violator, because it can be sued. But there's nothing private about this information. It's published, it is intended to be distributed. Okay, so I just mean that there's more and more, there's an explosion of data that people are trying to cope with that is potentially misusable, and that we don't really have an appropriate technological and conceptual infrastructure to deal with. That was the purpose for this project. Now, we can trust that this explosion of information will go on unabated, because there are very robust technological trends that create it. In particular, the plummeting cost of storage and the increasing power and ubiquity of networks are 2 trends that show no signs of abating. Okay, that was the motivation. So as I said, this was one of my first, in fact, this was probably my first experience with a very complex, ambitious, huge grant proposal trying to tie together lots of people. I worked with Dan Bonnet as my main partner. He was a wonderful person to work with. I think he was also one of Ninghui's postdoctoral advisors. So The academic PIs on this project are listed up here. The main institutions are Stanford and Yale. So I just want to emphasize, if you look at those people, if you know anything about their areas of expertise, we are not all security and privacy people. Included in that cast of characters are core database systems people like Avi Silberschatz and Hector Garcia Molina, and algorithms people like Ravi Kannan, and to a lesser extent, because he's also a database person, Rajiv Matwani. Okay, we also have 3 smaller scale participants listed at the bottom here, and one of them, Helen Nissenbaum, is actually not a computer scientist at all. She is a philosopher by training, and she has worked on what she calls value-sensitive design. How do social values get embedded in technology? Okay, so those were the funded academic PIs. We also had, from the pre-proposal stage, many other participants from companies, IT companies like Microsoft and Google. Actually, Kevin was not at Google at the time, he was at IBM. We had other parts of the university, like the law school and the medical school. The medical school, they actually deal with a great deal of sensitive data, and they have problems with all aspects of sensitive data management, both actually laying hands on the data you need to get and hiding the data you need to keep hidden. Okay, both of these things have to be brought together in this project, or we're really not going to make the kind of progress we need. Advocacy organizations like CDT and EPIC, these are user advocacy, consumer advocacy organizations. Okay, so these people were involved from the beginning, and I guess it's a testament to the compelling nature of our proposal that these were people who were volunteering they're not getting funded by NSF. They're volunteering to spend their own resources on our project because this is the kind of research they want to do anyway. Okay, so among the major research themes of this really long, broad project were massive data set algorithmics. So how do you cope with things like stream algorithms, sort of sampling algorithms? How do you cope with the sheer massiveness of the amount of data that is potentially relevant to whatever your task at hand is? If you're an intelligence community, if you're a epidemiological researcher, if you're a business trying to gather marketing data, there is the data. Relevant data used to be scarce and hard to capture. We now have the opposite problem. Data abounds, and it's extremely easy to capture them, and the trick is actually making sense of all the data you have. This was one of our main thrusts in the proposal, which was written right after 9/11, and when there was the pre-proposal anyway, when there was all of this discussion of the need to have more information about what bad guys are doing, and how we need to allow the intelligence community or the law enforcement agencies or the government to collect more information. The thrust of our proposal is no, you are drowning in information. Your problem is you have way more information than you can make sense of. What you need is a better technological and conceptual infrastructure for handling all this information. Okay, so sensitive data in distributed systems, that includes work on anonymity, both conceptual work on what exactly is anonymity in a network, what is pseudonymity, and analysis of specific anonymity systems like Tor, the onion router. SMPC stands for Secure Multi-Party Computation. This is a huge edifice in theory of cryptography that allows many parties, each with a relevant private datum, a private input, to jointly compute a function of all of these private inputs without revealing the private inputs to each other. There's a vast amount of theoretical work on this out there. It's not in use at all. We tried to make some progress on that, and at the end of this talk, I'll tell you why we more or less failed to make any progress on that. We have policy expression and policy enforcement tools for database systems. Helen's work is called contextual integrity. I unfortunately won't have time to explain that, but Helen is the one who was trained in philosophy. And recently, a big emphasis of this project has been on browser-centric defenses. So how do users protect their own personal information from all of the attacks and all of the basic natural tendency of this information to escape via browser-based interaction with other people? And how do users protect their machines from being attacked, taken over, and abused by machines that connect to their browsers? So client-side, browser-centric defenses. That's a very recent emphasis. Okay, there's tons, as I said, this is a very long and broad-based project. If you go to the Porsche website, which I already displayed the URL of, and which you can get to by simply Googling Porsche project, you can find a ton of information, including the educational information. We have a whole lot of courses and seminars that we developed. And we also ran a series of 10 workshops, sort of novel workshops on interdisciplinary aspects of sensitive data, including one on privacy and accountability. Okay, so what I'd like to do now, that's the general overview. I'd like to switch gears and briefly describe two recent technical contributions, both having to do with this browser-based defense. Then, if there's time, I think there will be, I will switch back to broad overview and maybe tell you in more free form sort of some of my conclusions, both about sensitive data and about what it's like to do this kind of huge project. Okay, for those of you who are interested in that, I don't know. All right, so the first piece of technical work that I'd like to describe is something called PWS. It's a Firefox plugin that stands for Private Web Search. Felipe St. Jean interviewed it, he's implemented it, he's my grad student, was presented at the workshop on privacy in the Electronic Society in fall of 2007. It was joint work with me and Dan Bonet, and also another one of my Yale students, Aaron Johnson. Okay, so the starting point here is that search is in some sense action central for internet activity. A lot of individual people's activity on the web and on the internet in general either starts with a Google query or somehow inherently and crucially involves Google queries, or more generally, crucially involves search. The plugin I'm talking about here works with Google, but there's nothing conceptually different about having it work with Yahoo. So I might say search or I might say Google, but same thing. Okay, for purposes of this technology. So I think it's pretty clear to everybody in this room that Google, or any organization that can collect a lot of information about what you search for, can learn a lot about you. And in fact, in some cases, that's actually Google's intention, is to learn a lot about you. Or in some cases, not. Okay, Google's intention, of course, is to sell ads. That might involve learning a lot about you. It might not. Okay, but if you actually make available to anyone a lot of information about what you are searching for, you are revealing a lot about you as a person and about your computing environment, about your information environment. Okay, so Felipe said, here's an example of his search history. What has he searched for recently? He is Chilean. He's a table tennis ping pong player. He's a Java programmer, and that he lives near New York. And so these are actually things he has searched for, and he convinced himself and all the readers of this paper that if he typed in just a subset of those search terms, table tennis, Chile, Java, security, sure enough, you get Felipe St. Jean's URL. So it doesn't take all that much search history in some cases to uniquely identify a person. Okay, and really, this is literally 4 queries. You could uniquely identify Felipe. And I don't think that's rare. I don't think he's being particularly exhibitionist in these queries. Okay, so we understand why one should be concerned about search, about information, personal information, and search. Okay, so what information does the search engine collect? I think that actually even saying search engine collect is making it both too intentional and too specific, because it's not only the search engine actually that is able to get information about you. But there's a lot of information that is sort of naturally revealed about you if you use Google in a normal browser environment and you take no action to prevent the flow of sensitive information in and out. Okay, so one type of information, I won't go over all of these sub-bullets, but one general type of information is TCP/IP sort of network layer information. Like obviously the IP address of where the computer on which the browser is running, that is something that is revealed. Okay. And that certainly makes sense. The operating system, I don't know why you would consider that a network layer, but I guess you could say the different operating systems have different sort of network interfaces. So that is in part network operating information. The HTTP headers reveal a whole different class of information. Like there's cookies that are sent back and forth to browsers. There's things about encodings and languages. What language is the query in? What language do you want the response in? What encodings can your browser actually display? So sort of HTTP interaction, sort of network application layer interaction reveals a different class or carries a different class of information. Now, this is actually quite well known. It's discussed in the security literature. There's nothing new about these observations. There's other stuff that is a big source of vulnerability and of revelation of personal information that was not very much discussed, which has to do with the HTML and the content of the page displayed in the browser. So a very big point, actually the main point of Felipe's project, was to take care of the fact that when a page is displayed in your browser, if it has active components like JavaScript, if there's any kind of programmable component that is running in your browser, it's essentially an unlimited conduit for information that resides in your machine. Okay? And so, the search engine itself or the originator of the web page can put an active component into this web page. When you load it into your browser, if you allow this, whatever scripting language it is to run, that script, that active component can suck all kinds of information out of your computer and report it to whatever server it is reporting back to. Now, I don't know why, but the vast literature on anonymizing browsers, this most important and biggest vulnerability simply was not discussed very much. So that was basically what Felipe dealt with in his project that was presented in his PWS project. Okay, so as I said, there had been a lot of work on this before. So various classes of approaches. So, and they're basically all about Firefox plugins, which is what Felipe's approach is too. But what do these plugins do? So there's one that's called TrackMeNot, that was also developed by a Porsche researcher, and characteristic of as a project as huge as this, it was not coordinated with other browser-centric work being done by Porsche people, but that's okay, because take different approaches, that's fine. We'd like to unite it all before the project ends. So Helen Nissenbaum, who is as I said, is not a computer scientist by training, and a computer science student, implemented TrackMeNot. Now the basic idea of TrackMeNot is that it tries to hide real queries in a sea of fake queries. It generates cover traffic. So a browser running the TrackMeNot plugin will, in addition to sending the real queries to Google, it will constantly be generating phony queries and sending them to Google as well. And the hope is that Google or whoever is receiving information from this browser won't know what's the real queries, what are the fake queries. So this idea of trying to hide legitimate traffic in cover traffic is, again, not new. This has been done on many different network layers forever. The problem with this approach is that it's basically very hard to model and analyze. It is quite difficult to prove that a particular algorithm for generating cover traffic actually works. It's hard even to formalize what you mean by works. Because in order to say this distribution of cover traffic interspersed with some real traffic is indistinguishable from a distribution of all real traffic, you would have to know what the actual distribution of real traffic is. And that's not something that we have particularly good models of for search and for actually lots of types of internet traffic. So in general, attempts to hide real traffic in cover traffic have failed. Serious, adversaries who try to strip out the cover traffic usually succeed. So in any case, that's one way you can try to approach this problem. And if you want to try TrackMeNot, it is also available on the Porsche website, and it's also very easy to use. OK, so a more standard approach to this, and also a more general approach, is to use Tor, which is a network layer anonymity system. Basically, what Tor does is it creates a version of onion routing or mixed networks. It creates a network layer solution that obscures the source address and the destination address of traffic. So you manage a source that's using Tor can manage to send to any destination, even one that is not using Tor. And all of the intermediate nodes will know where they got the packet from, where they're supposed to send the packet to, but they will not know the source address or the destination address. Okay? And that's a standard thing that's been studied a lot in the security literature. And it's a general network layer anonymity tool. So that other student I mentioned, Aaron Johnson, that's his main focus of his research, is modeling and analyzing Tor. So Tor, together with Privoxy, which is an HTTP level application, is a general way of achieving anonymous browsing, or so they think. It is not focused on search. Okay, and that was another innovation by Felipe, is let's narrow the problem just to search, and we can solve some of the we can take care of some of the vulnerabilities that exist in Tor plus Privoxy. So the good thing about using Tor plus Privoxy to try to achieve anonymous search or privacy-preserving search is that Tor is a good anonymizer. As research artifacts go, Tor is one of the best I've ever seen. It's a standard tool. It's stable. It's been in use for a long time. There's a lot of good people analyzing it. And so it's generally believed to be good at obscuring the IP layer information. And it's widely available, well supported. The bad thing about this approach is it's sort of awkward. Tor plus Privoxy together are not that easy to use, and I would say they're pretty much out of the question for completely naive users to use. And they also don't do anything about the actual HTML content loaded. They don't do anything to try to address that problem I mentioned before about eliminating JavaScript that could harvest information from your local environment and send it away. And of course they can't, because it's not a search application. It's a general anonymous browsing application. So there are uses of your web browser that necessitate your having active components in your browser. Okay. But usually search does not. Okay, so FoxTor is basically a user-friendly version of Tor plus Privoxy, but it still doesn't handle the active component problem. Okay, so what do we generally want to do? We want to take this general situation in which the search traffic that various users send back and forth to Google pretty much uniquely identifies them. And through the massive use, or through the non-trivial number of people using the PWS plugin, we want to make at least that set of users indistinguishable from Google's point of view. Okay? So there'll still be people not using PWS. They will still be distinguishable. But the plugin users should be pretty much indistinguishable. So, and as I said, there's various components to that. You want to make you want to standardize their HTTP header information. You want to obscure their IP addresses. And you want to make sure that the content that's loaded into their browsers doesn't identify them. 3 components. Okay. So I've already said that. This slide is sort of an anticlimax by now. But so the general way that this Firefox plugin works, now if I move away from this mic, can you still hear me? Yes? You can hear me? OK, good. So basically, the user enters the search query, and it goes into the well, actually, I can't do it easily from that angle. The search query is sent through the HTTP proxy. Now, what does the HTTP proxy do? That's this first sort of contact with the PWS plugin. The filter, the HTTP filter, deals with the fact that typical HTTP header information reveals a lot of unnecessary information about the searcher. So a PWS query, after it goes through that HTTP filter, will be very simple. It will be a single HTTP GET request that says, the host I'm sending this to is Google, the user agent is Mozilla, and I accept encodings, gzip, deflate, just some very simple encoding information. Whereas if you don't filter, if you look at what HTTP actually sends to Google, it contains much more information. It contains information about language, character sets, referrer URLs, plus just a lot more information about the user agent than is necessary. So the first thing that PWS does is standardize so that all of these queries, the header information looks basically the same. Okay? Next thing, send it through the Tor client. What does that do? It randomizes the source IP address. So by the time the query actually gets to Google, by the time the query actually gets to Google over here, the HTTP header information has been standardized and the IP address has been obscured. Now, that's been going on before in previous attempts. What's new is when the information is sent back, the search page is returned from Google, all of the JavaScript and other active components are stripped out. That's the HTML filter part. Okay? Then via the proxy, it goes back into the browser window and is displayed. Okay. So, it could be that there are some search pages that are returned. There are some return pages that will be useless to a searcher if they don't have the active components in them. But in that case, the searcher can simply reissue the query not using PWS, just using vanilla Google. The key insight here by Felipe is that most answers from search engines can be informative to the user without any active components running in the browser. So you can eliminate that vulnerability simply by being careful about filtering the return page. Okay, so that's the way it works, and more information can be found in the paper. I think I more or less already said which components handle which problems, so I won't go over that again. Let me just point out that there is obviously one remaining problem, and we make no bones about it in the paper. We did not set out to solve this problem. I believe that Chris is now solving this problem. So any day now, this is the main problem. You might go through dealing with all your IP layer information, your HTTP header information, your active components problem, all of that, but the actual content of the query still reveals who you are. Okay? So if you notice, Felipe's query information, even if he used PWS, it would still identify him. Okay? You could take any browser. In fact, it didn't have to be Felipe. Anybody could type in those queries. Google would have no idea who's doing these queries. But to the searcher, Felipe would still be identified because the answer to that combined query was Felipe's homepage. So, Google, if it really wants to know Felipe's interests in life, will know that it is returning that homepage and could keep track of that information. So the remaining big problem is how do you actually sort of privatize or somehow sanitize the content of the query. This is a huge problem. It has many variations. And we haven't solved that yet. Okay. So plugin installation, you can just go to the tools and extensions, select PWS and drag it. Once you've done that, you get a search option that is PWS Google Search. It's very easy to use. Felipe is now working on getting the Firefox people to officially adopt it. And basically, we have these open problems, that one of which I already went over. That's the first bullet. It would be nice to be able to formally, once we try to tackle the first bullet, it would be nice to have a formal model in which to analyze how well we're doing. There's still an issue with Tor, that the Tor path selection does have quite variable performance. Okay, and you can thus get variable length of search time, much more so than you would if you were not doing it anonymously. But I think this is actually true of all the anonymizing search tools, certainly all the ones that use Tor. So anyway, main thing is, I encourage you to try to use this. It's available on the Porsche website. There's the URL, but you don't need it. You can just go to the Porsche website and click on software, and it'll tell you how to get PWS. It's very easy to use, and it really does address many of the qualms that people have about non-anonymous browsing. Okay, so that was one of the two client-side defenses that I wanted to talk about. And the other one has to do with cross-site scripting. So I should have put, okay, so switch in the slides. You had my vanilla slide technique at the beginning, then you had those beautiful slides prepared by Felipe. Now you have a different style of beautiful slides prepared by Dan. And then at the end, we're gonna go back to my not so beautiful slides. Okay, so I should have put the names on this page. I forgot to do that. This stuff I'm going to present now, I'm only gonna present a subset of it because it's actually a fairly big paper, was presented at the CCS 2007 conference last fall called Protecting Browsers from DNS Rebinding Attacks. It's by Dan and his students, and the students involved are Colin Jackson, Adam Barth, Andrew Bortz, Weidong Xiao. So Colin Jackson, one of the reasons I wanted to mention those names is Colin Jackson is now a Stanford PhD student working with Dan. Before he was a Stanford PhD student, he was a Yale undergraduate. And this has been one of the nice things about the multi-institutional sprawling nature of this project, is that we get to have like undergraduates from one place go to graduate school at the other. We've had various graduate students go on to be postdocs with a different investigator at a different institution. And the sort of multi-advisor and multi-institutional advising of students and postdocs is a great advantage of these huge projects. It's compensated for by some disadvantages, but it's a great project. Okay, so XSS stands for cross-site scripting, and the main take-home message of this chart is that internet vulnerability is sort of migrating to the browser. Okay, a lot of the problems, the botnet problems and other internet abuse problems, malicious traffic problems, are being launched through browser vulnerabilities. So this part of the client-side defense story is less about protecting an individual's personal information or identity than it is about stopping an individual's browser from being hijacked to launch an attack. So it's protecting the network from browser vulnerabilities, which is another side of, which is different from protecting an individual from browser vulnerabilities. Okay. So it's known that you have, there's potential problems with different sites being accessed in the same browser session on one machine. And the way that browsers generally try to deal with this is what's called the SameOrigin Policy. So those of you who have tried to teach, who have taught non-majors or even undergraduate majors about the web, have probably introduced cookies, explained what cookies are, either in a purely technical or a sort of more social level, and probably you've slipped in the fact that a cookie from site A is not supposed to be accessible by site B. Okay, this is just considered to be a general good hygiene practice because site A is storing potentially sensitive information in his cookie, and it's supposed to be used for his business purposes. It's supposed to be used to improve the performance for his server and this user. It's not supposed to be a general repository of information for any site that is accessed from this browser. Now, the problem with SameOrigin policy is that it's coarse and it's vague. It's coarse in that it's a very coarse-grained, not that it's obscene. It's coarse-grained policy and it's ill-defined. So in general, what we mean by SameOrigin policy is that two sites are supposed to be considered the same by a browser if they have the same domain name and port and protocol. So you can see right off the bat there's something wrong with this. This doesn't really capture the idea, because that would mean that Amazon.com and Amazon.co.uk were not the same origin, because they have different domain names. Now, in fact, they are two sites owned by the same company. So there is no logical reason that they should not be able to read each other's cookies. But a straightforward application of SameOrigin policy would not let them do so. Okay, but in any case, this is out there and it's been in use for a long time, and it has certain advantages. It's supposed to protect cookies from being shared rampantly, and it's supposed to be able to keep sensitive documents behind firewalls. So we presume that some potential theft of a document, some potential thief of a document would know the URL of that document. He'd know the IP address of the internal machine. But if the browser enforces the SameOrigin policy, he's not going to be able to read it, because his IP address won't correspond to the IP address on which this particular document resides. Okay? So, this has various problems, one of which I said is just with this vagueness of what does it mean and with domain names, but it also just is basically very hard to enforce. You have some script command on a page, and that will give full control. It'll give full control to the script, which will blow away, whatever origin policy you're using. There are also so in other words, it could be that the page comes from the right origin, but it enables the browser to run code that comes from some other origin. Okay, so the browser doesn't do any more IP address resolution. It simply takes this HTML element, this HTML command, and executes it. So it sort of subverts the SameOrigin policy. The other problem with the SameOrigin policy is that it just really thwarts some very obvious things you want to do. Like, there are very legitimate reasons for sites to communicate via a browser. Like with Google AdSense, for example, that's exactly what they want to do. Okay? They want to have various advertisers put active content onto their site, and they want one browser to be moving information between the advertiser and Google. That's the whole point of Google AdSense. So to have a browser security policy try to stop that is sort of silly. Mashups, that's sort of an entertainment, sort of user-driven entertainment application in which the intent is to get different content from different sites into the same browser window communicating. Okay, so what you really need is a much more sophisticated idea of security. You need an operating system like security that can operate in the browser environment, so shared memory, inter-process communication, etc. And this PAMI, I don't know what this acronym stands for, but that's Dan's expeditions pre-proposal. So that's exactly what they're trying to do, is to develop a full-fledged OS-style security framework for browser-based activity. Okay? All right, but in the meantime, they did this project in which they addressed what's called DNS Rebinding Attacks, which is one way to thwart the SameOrigin policy and sort of undo the security that it provides, even in the environments when it should provide it. So not the Google AdSense environment, for example. Okay, so the basic rebinding attack is not new to this paper. It was given originally, as far as we know, in a paper by Dean, Wallach, and Felton in 1996. So obviously, evil.com is the bad guy, and the goal here of evil.com is to exfiltrate, I think that's a beautiful word, to exfiltrate a sensitive document on this internal server behind the corporate firewall. So the evil.com guy knows the URL of this document, but he just doesn't, he will not be able to actually extract it from the firewall. Okay, if he gets this innocent user to go to his site and he tries to access this document and the browser will say because that violates the SameOrigin policy. So how can he get around that? It's called DNS rebinding. So somehow evil.com, who is running both a name server and a web server, and there's nothing wrong with that. You're allowed to run your own DNS server. So we're not talking about corrupting someone else's DNS server, which is a potential problem as well, but it's more complicated. So evil.com somehow gets this innocent user to go to evil.com, so to issue a DNS request to go to evil.com. So first time that happens, she goes to the name server the DNS server that's being run by evil.com and gets the IP address of the evil.com web server, okay, and that's a time to live field of 0. So the purpose of the time to live field of 0 is to force another DNS lookup, and that's when the DNS rebinding happens. So first time this IP address is used, the innocent person goes to the actual evil.com web server. They load some stuff into her browser, which causes her to look for a document, okay? And supposedly the source of this document is evil.com, but it was time to live 0, meaning when she goes to look for this sensitive document that is actually on the corporate web server, but that she is going to search for on the evil.com website because of this iframe source equals evil.com thing that the evil guy has loaded into her browser, she does another DNS lookup because the first one had a time to live 0. So she has to go and get a document from evil.com. She does another DNS lookup. This time, the evil.com web server tells her, look at the corporate web, gives her the IP address of the actual home of the document. Now, this allows the evil.com guy to say, get that document and feed it back to the server. Now, why does the browser say, violation of the SameOrigin policy? Because at this point, both IP addresses are hooked to the same domain name, the same port, and the same protocol. They both got hooked. The two different addresses got hooked to the same domain name because two different DNS lookups were done. Okay, so that's been known for a long time, and it's just very simple. It assumes a lot of stuff that you don't actually need to assume. You don't actually need to assume that this DNS server knows the URL of the sensitive document. He could figure that out once he's got the content onto her browser. Okay, so. One thing they try to do to prevent that is called pinning. If you look at a number of popular browsers, they don't accept TTL0. And regardless of what the TTL is, once you do a DNS lookup, they actually pin that address to that domain name for a certain amount of time. IE 6 and 7, for example, pin for a very long time. Okay, now, so that means the second connection to evil.com would go to evil.com, even though the first one said TTL0. Okay, so the problem with this is that it's really not tenable. You cannot force browsers not to never reissue a DNS lookup. Suppose you have an error. Okay, suppose you have a crash. Regardless of what the pinning database does, the browser is going to have to do another lookup. Okay, another thing is that sometimes you can't actually pin an IP address to a domain name because some browsers do various things. In fact, many browsers do various lookups through a web proxy. So the browser that actually displays the content never actually knows the IP address. It's the proxy that knows the IP address. So pinning is not a panacea. So I see I'm getting short on time, so I won't go through this next slide in detail. But the gist of it is that this is more complicated because there are plugins and applets and various modules like JVM and Flash that do their own pinning and that have a lot of power. In order to function properly, they are allowed to open socket-level connections to servers in order to get streaming content and send streaming content and stuff like that. So simple pinning simply won't work. It would basically trash a lot of common applications. So I'll skip this. OK, so all of this is theoretically possible. DAN students came up with, if you read the paper, they come up with at least 10 variations on the basic rebinding attack. Many of them take advantage of these applets and plugins that do a lot of socket-level connection and have a lot of power and maintain their own DNS bindings. OK? So how common is this? It's extremely common. They ran an experiment in which they bought a few ads, okay, and tried to lure unsuspecting users with all of these DNS rebinding problems in their browsers to their ads, and they were very successful. Okay, in 3 days, for which they only had to pay $30, they were able to take over 40,000 browsers. Okay? And once you take over these 40,000 browsers, as long as that particular browser connection is open, you can do a tremendous amount of damage. Okay? A chart that sort of brings this home is traditional botnets tried to exploit things like buffer overflow and other bugs in widely disseminated code, and those were disseminated by things like spam. And once you actually compromise a computer, which you can do to many of them, it's sort of permanently compromised, or it's compromised until somebody figures out that it's been compromised and patches it, actually removes the malware that was implanted or somehow isolates it. Okay? With this browser-based thing, it's different in that you don't permanently compromise the machine. You just ephemerally, just temporarily hijack the browser connection. Okay, but the really amazing thing about this is that you can take over many, many more machines because it's very, very cheap to buy ads by the impression. Okay, and you can apparently lure a whole lot of browsers to your site and start basically exploiting these DNS rebinding attacks. Now, each one of them is only available to you temporarily, but you can take over, more or less the whole internet for the amount of money that you would spend on constructing a large botnet using old-fashioned methods. So the gist of this paper is they have a few simple tools that prevent the obvious rebinding attacks and some of the non-obvious rebinding attacks that they were able to come up with. Okay, one of them is they built a DNS firewall, DNS perimeter. Okay, it's called, I think, DNS wall. And it integrates very easily with the DNS server. This was commissioned by some DoD agency. I don't remember which one. And the essential gist of DNS wall is it causes the browser never to bind an external domain name to an internal IP address. So sort of an obvious idea, but the state of our browser software is that that is not automatically done. The way DNS works now, you can get a browser to bind an external domain name to an internal IP address. So DNS wall, implemented by Adam Barth, prevents that. Stronger defenses, they built something that basically ensures that the GET request is accurate. So if I have somehow managed to rebind evil.com to Google, and they did exactly that, and were able to commit click fraud, okay? So it's not like browsers are especially on the lookout for Google rebinding. It's just very easy to implement DNS rebinding attacks. So if I have somehow managed as a bad guy to rebind evil.com to the Google IP address, and then that unsuspecting browser issues a search query to Google, the header might say get/host:evil.com. this should be something that you can, notice. So you can block socket level access. You can make sure that the host header is correct. Okay, that if you're actually sending something to Google's IP address, that you don't have some other domain name in your HTTP header. Okay, so they implemented that. Okay, and that was actually adopted by Sun. Okay, you can no longer, the JVM no longer opens sockets in which there's some mismatch between the host being connected to via the socket and the header information. This is actually an officially adopted simple piece of code that the Stanford students wrote. Okay? And that's October 27th. So that's a recent adoption, and it was like right about the time they published this paper. So it was apparently a very convincing application that they wrote. Okay, you can make sure that you do some kind of hostname authentication. Okay, the host can publish 2 reverse DNS entries. So you have the IP address, and you also have a DNS entry that has the name, the domain name, and the IP address. Okay, so the browser actually looks for the connection in an official DNS entry published by the host of the domain name it thinks is supposed to be bound to this IP address, evil.com. It doesn't see that. It sees bank.com and this IP address, and it says, this is a DNS rebinding attack. I'm not going to issue this connection. Okay. So they implemented that. I don't think that Sun has officially, or that anyone has officially adopted that yet, but it's actually a very simple thing, and I'm sure that Firefox or somebody will adopt this. Okay, so in summary, they have proven by doing an experiment that it is very easy to do a lot of DNS rebinding. Okay, browsers are genuinely very vulnerable. It is very easy to lure unsuspecting browsers by using ads. It is very easy to lure unsuspecting browsers to your evil servers that can perform these DNS rebinding attacks. It's not just a theoretical problem, it's a real problem. There are some simple fixes that they've implemented, and a couple of them have actually been officially adopted. All of them are available from the Porsche website. So if any of you want to protect your own browser, by all means do so. And this is the URL for this particular stuff, but you can get there from the Porsche software page. And finally, just again, this POMI, that's Dan's expedition pre-proposal, they hope to take this beyond the simple fix level to a robust, meaningful sort of OS-like security framework for browsers. Okay, so those are the 2 pieces of technical work that we've been doing recently that fit into our recent obsession with client-side defenses, both against misappropriation of personal information and against hijacking of a browser for network attacks. Okay, there's other client-side defenses. I shouldn't actually have said more Porsche anti-phishing tools. It's more Porsche client-side defenses, because that last thing wasn't really about phishing. And these are actually all about phishing. Dan's students have implemented 5 different anti-phishing tools, also all available from the Porsche software page. All right, so switch gears. I had told you that this is a very broad-ranging project, and I went into 2 examples of work we've been doing on our recent obsession with client-side defenses against various misappropriation of personal resources. We really have worked on almost all aspects of sensitive information management over the course of this project. Both how do you actually get at and process the sensitive information that you do need, and how do you protect your sensitive information against misuse by people who don't need it. Okay? So among the other things that we've done, should say those 2 things I just presented were extremely practical, implemented and deployed browser plugins and firewalls and stuff like that. Probably close to half of the work in Porsche has been theoretical. It's been algorithmic and analytical work, okay, in algorithmics and databases. Okay? So one thing we've looked at is stream algorithms for massive graphs. Okay, so you might say, why are we interested in massive graphs? Well, actually, massive graph information captures a lot of what people do in today's information environment. The web itself is a massive graph. Web searching and the Google's original PageRank algorithm is in part a massive graph algorithm. So we've been looking at stream algorithms. For those of you who are not already familiar with the whole stream algorithms thrust of research lately, I won't be able to define it. But nobody had looked at graphs. Everybody had looked at numerical data, frequency moments, L1 differences, stuff like that. We were the first to look at graphs and combinatorial problems. There's also a lot of work that was done on massive matrices by my colleague Ravi Kannan and his students and postdocs. So that's in the line of actually being able to retrieve and process the massive amounts of data that we have theoretically available to us now. There's part of what we do with sensitive data is we look at domain-specific sensitive data. So we have a big project that's been supervised by Avi Silberschatz going on with the Yale Center for Medical Informatics, where essentially medical informatics people have been trying to use off-the-shelf database products for many years. And off-the-shelf typical database query engines, typical database schema are simply not appropriate for medical data. So John Corwin is a Yale graduate. He's Yale graduate student. He's finishing this year. He implemented a new query engine that is suitable for medical informatics data. I mentioned Helen worked on contextual integrity. This joint project with Adam and John applied her notion of contextual integrity to financial and health regulations, to Gramm-Leach, Bliley, and HIPAA, saying, okay, formulate a logical formula that captures the goal of this legislation, and then encode the actual legislation in this logic, and see whether the former subsumes the latter. Because if not, then this legislation is actually not, even if perfectly enforced, is not actually going to have the desired goal. So they applied logic and the theory of contextual integrity to actual laws, actual US laws about sensitive data. So I just have a few more slides in which I want to show you a whole other type of investigation we did, and then I'll wrap up. So this privacy-preserving survey computation. So I mentioned at the beginning that sensitive data in distributed computation was one of our areas of concentration, and that included secure multi-party function evaluation. So you have n parties with x1 through xn private data. And there's this huge theory of how do you execute an n-party protocol at the end of which everybody knows f of x1 through xn, but player I doesn't know xj. Huge theory, it's not used. So Felipe, same one who implemented PWS, and some others, we actually implemented a specific case of this motivated by the Tolby survey. So before 2004, I know those of you who are faculty members know that the Tolby survey is this vast survey by the Computing Research Association of statistics about computer science departments, the most interesting ones of which are faculty salaries. Okay, so they used to get from every department, this is by rank. The departments are striated, are stratified by rank. Within each rank, okay, that's the tiers rather, are stratified by tiers. Within each tier, every department divides up the faculty by faculty rank, and they reported the minimum, the maximum, the median, and the mean of the salaries within that rank. So rank means assistant, associate, full, etc. So the CRA used to try to compute various statistics from that meager amount of data. And in particular, they wanted to publish the mean salary of all departments, with the mean, say, associate professor salary of all departments within the second tier. Now, if you notice, there's a problem with that, because you cannot actually compute the median from those inputs. And in fact, the whole old survey was riddled with like serious technical problems. So they decided in 2004, and they announced they're going to ask for complete anonymized salary lists. Okay. Now, this to Porsche researchers, this threw up a huge flag because there was already resistance to releasing any salary data. Asking for complete salary data, even without names, was going to cause more resistance. And in fact, even for department chairs that might have been happy to comply, it's often forbidden by the school. Okay? So, and in fact, Yale and Stanford are two schools that have explicit policies that you cannot do that. Okay? So, we implemented privacy-preserving survey computation. We made it available to them. I won't say how it was implemented. It's a huge Megillah to explain what secure multi-party function evaluation is. And those of you who know it already know it. Those of you who don't know it aren't going to get it in a 1-minute explanation. But Felipe implemented a really nice special case of this that would have been very easy to adopt, offered it to CRA, said this will at least encourage compliance. Departments, if they understand what privacy-preserving multi-party function computation is, and we can explain it to them if they don't, they will trust that they can reveal this information to this particular application. The results will be computed. The raw data will never be transferred out of the client machine. Okay, so second to last slide. We hand them this open source, user-friendly, free implementation. They don't adopt it. I say this is the heartbreak of cryptography because if you've heard a lot of crypto talks over the years, honest people will have told you this is usually what happens. Okay? A crypto researcher implements one of these spiffy protocols that has been written about in the crypto proceedings, makes it available, and it's not adopted. Okay, so CRA, I don't have time because I'm already 5 minutes over time, but CRA had a bunch of reasons for not adopting it, some good, some not good. The not good one is they said, oh, we'll get good compliance anyway. And in fact, they later said, we got good compliance anyway. 83% of the departments complied. Now, what they didn't say is, of the 17% that did not comply, or of the 83% that did comply, how many of them were public universities in which salary information is public anyway? So in other words, it might be exactly the non-compliers who are the ones you needed the data from. Okay? And in particular, how many Tier 1 departments didn't comply? Because this will completely screw up the Tier 1 data. If more than half of those departments didn't comply, then they are only averaging the ones that have public salary data anyway. Or they're only reporting on those. Okay, so that was a problem. Interestingly, we also had resistance from the universities. So I went to the Yale Provost's office. I explained what privacy preserving, basically it's this general technique that allows people to use data without revealing it. Allows you to do a computation on private data and get a result without ever actually getting access to the clear text data. So their answer was, well, that may be true, but I suspect that I would still be violating our policy if I use that software. I would have to have that software evaluated by some expert. And after all, whom could I hire to evaluate such a thing? This is not something I've ever seen before. It's very hard to evaluate correctness and security claims. And finally, what's the point of my making a decision to do this? This only makes sense if the entire Ivy Plus peer group adopts this simultaneously. Okay, it doesn't make sense for Yale to provide this data and Harvard not to provide these data. If they're going to do this survey, they're going to need adoption by all of us. So we'd have to make a joint decision. It's not a decision I can make. So, really, really sobering experience with the idea that we can, as technologists, fundamentally improve the state of the art of handling of sensitive data. This seemed like a very simple, application where the technology is very well understood, the protocols are very well understood, and the user community is quite small. Okay, it's CRA member departments. It's not something we have to explain to all internet users, and we got nowhere. Okay, so that was one of the least successful parts of Portia. This client-side defense stuff is some of the most successful, and there's everything in between. All right, so last slide, and I'm only 5 minutes late. Good. Okay, so our main conclusion is that this is a very, very tough situation to make headway in. There is really less and less sensitive information that is truly inaccessible. The question is the cost of access, and that cost is going down. And it's going down because of robust technological trends that we cannot stop. The legal support for when do you reveal data, when do you not reveal data, how do you protect data, what do you report, whom do you hold accountable, that whole legal structure is not in place. So no matter how much technological progress you make, and progress is still being made, okay, you may not really be able to improve this vague sense that people have that there's all kinds of information about them out there and they can't control it, because you need not only better technology, but an appropriate conceptual and legal framework, which is not in place. And finally, this whole client-side defense, which is a technological triumph, I think can really only go so far, because while you might be able to prevent by using client-side defenses, you might be able to prevent the exfiltration of information that will allow people to develop very fine-grained profiles of you. The coarse-grained information about you is enough to make you vulnerable to a lot of nuisance activity on the internet. People don't have to know your entire search history. People don't have to know your entire medical history in order to be able to bother you on the internet. If they know your name and address, your name and your email address and a few things about where you work, you can be quite vulnerable already. So, I think that at some point we're going to have to move beyond trying to hide information and try to come up with a good and enforced regulatory framework about use of information. Those are my preliminary conclusions. Thank you.